So, have you people seen any of Manjul Bhargava's talks? So he keeps giving this problem in most of his talks. Very interesting problem, which I think arose in Sanskrit poetry. Okay, so I'll say that problem to you. You can try for it. You can work on it. So it is like this. In Sanskrit poetry, there are like two syllables. So when you say this short and long syllable, is it ka, a and a? Is it like that, or is it something different?
That only.
That only. Okay,
my
fine.
understanding also that only. Yeah.
So what is the name for that?
I think it's Laghu Dhruta.
Laghu and Dhruta.
Laghu is short.
Okay, so you know what is Laghu and Dhruta?
Yes, sure.
Okay.
Yeah.
Right. So Laghu is on short, is a short sound, and the Dhruta is a long sound. And it is taken that the short sound takes one beat, and the longer sound takes 2 beats. Okay. So when you're reciting the form of a poem, the short thing takes 1 beat, and the long thing takes 2 beats. 2 beats is some unit of time. So now the question is, a poet is composing a poem, and then the poet sees that there are still 8 more beats to be filled. Okay, 8 more beats to be filled. And how many different ways can you fill that 8 beats with this Laghu and Dhruta? So it could be 4 long, or it could be 8 short, right? But then there are other combinations also, right? Long, short, right? So the question is, how many different ways are there? Yes, Sunil, that is correct. But here, for example, this case of 6 short and 1 long, right? That long could be in the first position or the second position or third or the last, right? So each of them are counted as a different case.
Okay. So then there are so many cases, right?
Yes. So this actually, Manjul Bhargava says that poet named Hemachandra, he poses this puzzle, and then he gives a very interesting solution to it also. Okay, yes, this will solve the problem.
Yeah.
Right. So you're asking for a explicit formula, right? For this.
Explicit formula, yeah.
Fine.
One more thing. So in the West, how did they come up with this series? What was the root? That rabbit thing, is it?
That rabbit thing, yes. But I felt it as a very messy problem.
It is very contrived. It's not so natural like this one.
Yes, exactly. Because there are lots of interesting properties associated with it, lots of properties. We will explore that also. Okay. But before that, for the question which you had asked, I'll try to provide a hint. But this is a bit involved. This thing. We'll see. I'll try my best. Right. So this technique of finding this explicit formula, no, I think it dates back to Euler. A very ingenious method.
Okay.
This method is called the method of generating functions. You might have definitely heard of it in your engineering days. So this method of generating function, right? It looks in the beginning it might look very strange. But surprisingly, it is a very powerful tool. Mm-hmm. So what Euler did, I exactly don't know for which problem he applied this method. So we'll just call the numbers in this sequence. So now Okay, we'll just call the sequence to be A naught, A1, A2, A3, and so on. We can keep A naught to be 0.
Okay.
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 So, what order to was consider this infinite series.
Okay.
K is 0 to infinity. Yeah, already we have so much of trouble with infinite series. And then he takes that infinite series with this AIs as coefficients. So the series is like this: A naught plus A1x plus A2x squared, and so on.
Okay.
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 Right. So now for the sequence under study, the sequence which you are studying now. Okay. We'll call. Is there a value of x for which this sequence converges? So we'll call this as f of x.
Okay.
Okay. So f of x is a particular value only if this series converges, right? Otherwise, this f of x doesn't make sense. It is not a number.
Right. Right.
Right. So first question is, can you find a value of x or a range for value of x for which this series converges?
Okay.
Don't ask me how will this give me an expression for AI. You'll be very surprised if you cross this big obstacle, then you'll see.
Okay.
So recently, wrote a book on combinatorics, and the name of his book is Generating Functionality. So generating functionality is not a standard word in maths and all.
Oh.
But because of the central importance this method tool plays, he named that book on combinatorics as Generating Functionality.
Okay. Sorry, who was the author?
Author, I don't remember. I'll check and let you know.
Sure.
So, given a series, how will you decide if it's correct or not? That is one question.
Try to find the general formula for sum of n numbers of the series and see what happens when n tends to infinity.
Wonderful. Wonderful method. Yeah, so this is what we did for geometry series, right?
Yeah.
But what happens is finding a closed form expression for for n terms, right, is not always easy. In fact, in most of the cases, it is almost impossible.
Okay. Then looking for bounds, like we did for the
harmonic series.
Harmonic series, yeah.
Yes, excellent.
Okay. So this f of x can be broken up into a sum of different sum of multiple geometric series. So so we would have x plus x squared plus x cube plus x to the power 4, etc., etc. Then it would repeat again, starting from say x cube plus x to the power 4, and then another geometric series that would start with x to the power 4, etc. So
wait. So what do you do the coefficients A1, A2, A3 and all?
That is determining how many times that term will, in how many of those geometric series that term will repeat.
Oh, okay, great. Nice viewpoint. Nice approach.
So each of those geometric series will converge if x is greater than 0, less than 1. So this f of x would also converge in the same range.
Wow, what a argument.
No.
No, I'll just So if it had been a sum of finite number of geometry series, then it is clear. This argument is like clearly finish it off. But here it is a question of infinite number of infinite summation, right? So I'm just thinking, no, again, it doesn't close the door, but you have to be a little careful, right? So that's why I'm just thinking about it.
Okay, yeah.
So again, so if you're able to give a proper definition of what we mean by convergence, then we can compare your argument with against the definition and see, right?
Right.
And then it will be clear whether this argument is actually correct or not.
Okay.
Okay, so can you try to think along that line?
Okay. So the first thing I tried was -1, but that doesn't work out.
Yeah, -1 is also very interesting case. Actually, this divergence series, right? A harmonic series, we just closed it off saying that okay, this just divergence and we left it, right? But divergence series by themselves are very interesting objects of study. In calculus and analysis, but I have not gone so far along that direction.
Okay.
To give one example, you might have heard of Ramanujan's formula: 1 plus 2 plus 3 till infinity is -1/12.
Yeah.
Okay, yeah. So this is not a funny formula actually. It has a meaning, but if we take the meaning of infinite sum as some sort of convergence, then definitely this doesn't make sense. But there's another meaning to it. Yeah, so in that realm, this makes a lot of sense. This is, I think, in somewhere related to Riemann's zeta function. Yeah. Anyway, yeah. So, but my point is that divergence series are also like having sailed upon by people.
Okay.
For reasons not so clear to me. I'm not explored divergence series as much.
Okay.
I just feel like asking a question to you. So, you know what is this closed form expression for this series, right? The geometry series. Right? Now, if I consider 1 plus 2x plus 3x squared plus 4x cubed and so on.
Okay.
Okay, so if you take x less than 1, or 0 to 1,
yeah,
then see if you're able to compute.
Okay.
Okay, analyze this series first, and if possible, to compute the value of it.
Okay, yeah.
Yeah, but yeah, so the method the ingenious method which you gave, right? Yeah, that worked very well here.
Okay.
Sunil, for the beat problem, if you want any hints or if you have any comments to make, you can make anytime.
Yeah, she actually trying to list all possible ways.
Exactly, that is the way. That is the way. And then once you list down all the possible ways, then the pattern will emerge.
Okay.
So there is this. Have you heard of this Basel problem? This name Basel problem.
Basel.
Basel is actually it's a name of a place in Switzerland. So I think one of the Bernoulli brothers. Bernoulli family is a family. It has contributed lots of mathematicians, lots of first-rank mathematicians, and one of the Bernoullis posed this problem. So there is this. Since we're talking about infinite series, we have this famous series. So yeah, Sunil, if you're not familiar with this series, you can just ignore. You can just listen to the story. People try to find this value. People are just trying to study this infinite series, and then Bernoulli, and then people found an answer. They were able to determine the properties of this series, and then Bernoulli asked this question: You are able to see the pattern here, right? So what is the sum for this? Can we give a closed form expression for this infinite sum? So this problem was known as the Basel problem. And a young Euler, I think he was in 16 or 17. So he was actually collaborating with one of the younger Bernoullis. And at that time, he came to know about this problem, and he tried to solve. He worked on this problem. He worked on this problem for some time, and he came into mathematical timeline by giving a closed form expression to this formula. And actually, what he did is what legend says is he evaluated the value of this series till 50 decimal points, 50 decimal digits of the decimal point. He evaluated its value, and then he says that the formula just came to me, and surprisingly, like math keeps throwing such surprises on us. This value is pi square by 4, if I'm not mistaken. Don't ask me how pi came here. Wait, let me just cross check. What is the value of this? Okay, yeah. Pi square by 6, sorry, not by 4. So Euler, he first evaluated its value till 50 digits on a decimal point, and then he was able to show that this series actually has its value pi square by 6. Wow.
How is this related to pi?
Don't ask me, ask the masters. Yeah. Yeah, so the reason why I told the story is like, yeah, Euler got this by doing a lot of groundwork. 50 digits he calculated, right? Yeah, so this is the way usually we start working. There are lots of experimentation, trial and error, and the final result comes only late. And yeah, I don't know how pi square by 6 came here. So have you heard of the Riemann hypothesis?
I've heard, but I don't understand now.
Okay. The greatest unsolved problem now, currently it is one of the most important unsolved problem. So that problem has its roots here, you can say.
Oh, is it? Oh.
Yeah. It's not directly, but this kind of crazy submissions.
Yeah, Shiva, after exhaustive list, I came up with this number. I don't know, 34.
34. Just a minute. 34. Wow. Yes.
Yeah. There were like 5 ways. I mean, 8 short, 4 long, 6 short, 1 long, 4 short, 2 long, 2 short, 3 long. So then for each one, I made a exhaustive list.
Great. Wonderful.
Yeah.
Wonderful. Right. So,
but
yes.
I mean, I could not see any pattern. Shiv.
Yes. Okay. Now, so the problem is very specific to 8 bits, right? We will call this the number of combinations for 8 bits. We'll call it F8. Number of combinations for 8 bits. We'll call it F8. Okay. So now, suppose we know the value of X6 and F7. Somebody has already computed it. Now, using these two, can we immediately find out the value of F8?
Okay. I think need to find out what is F6 and F7.
No. Suppose we know, I'm sure you can find out what is f6 and f7. But suppose we know the values of f6 and f7. Using that, or we need to find the value of fn. We need to find the value of fn, and we know all the values from f1, f2 till fn minus 1. All these are known. Okay, with this being the case, can I find out the value of f of n without an exhaustive search?
Sure. Sure. I just calculated the values for f1, f2, f3, f4, and f5. I mean, I could quickly calculate it.
Brilliant.
I mean,
What did you observe?
Yeah, f1 is 1, f2 is 2, f3 is 3, f4 is 5, and f5 is 8. So, yeah, I know I got it. It's a Fibonacci sequence, right?
So how is Fibonacci sequence coming here?
Yeah.
Can you explain how Fibonacci sequence is coming here? So each sum, so the number of combinations for n is the sum of the number of combinations for n minus 1 and n minus 2, right? Yeah. How do we understand? How can we understand this? So this is one strategy generally when mathematicians work, right? They follow this, and many great mathematicians have mentioned this, that when they're trying to solve a problem, and if the problem is hard or the progress is not much, they try to simplify the problem. They try to keep simplifying the problem till they come to a problem which they can solve.
Correct. It is recursive, right?
Recursive. So why is that recursive? Is that, I mean, can you explain that? In fact, as I was saying, Sanskrit poet named Hemachandra, he poses problem.
Okay.
And he gives a one-line solution to it. And this is why Manjul Bhargava later he names this as Hemachandra Fibonacci sequence. So the name Fibonacci has come because it arose from the problem which Fibonacci gave, from one of the problems which he gave. And Manjul Bhargava says that Hemachandra came much before Fibonacci. So we will name this as Hemachandra Fibonacci sequence. Yeah, but changing a name, even if it's officially changed, changing it in the minds of the people will take long time. It may not happen also. So the same thing happened with the Hindu-Arabic system, the name. So when the Arabs took this to Europe, it was named as the Arabic numerals, because the Europeans got it from the Arabs, right? And this name remained till early 20th century. The numbers which you write were called as the Arabic numerals. And it was the American mathematicians in 20th century who were interested in the history. It was they who said that, okay, it's not Arabic, it is Hindu Arabic, because the origin is Indian. Yeah, so it took American mathematicians' intervention to tell this to the world.
Do you know Hemachandra's verse for this Fibonacci sequence?
Hemachandra's word?
Verse, the text he used.
Oh.
In one line it was captured.
No. Okay. Actually, Manjul Bhargava might know. and if I meet him, definitely I'll ask him and I'll let you know. Yeah, so at this stage, you can just think about this relationship, how this is coming about. And the Hemachandra's one-line solution is exactly explaining this relationship. Yeah, so why it comes. So we'll discuss it in the next session.